All right. Now we're going to talk about our storage nodes. Again, the storage nodes store all persistent PanFS data. Each storage node is a computer that acts with other nodes in the realm. The storage nodes are also called OSDs, object storage devices. Storage node usually refers to the hardware. OSD usually refers to the node's logical role in the system. We currently offer two types of storage nodes. Actually, this is soon to be, well, we still type. We have ultra nodes, which are a number of different flavors. ASU 100, ASU 100 extra large, and AFA 100 storage nodes. Soon to be released is our Echo nodes. And we have classic storage blades. And some of you have experience with the classic storage blades. We will not cover those in this course. We will focus on the Ultra. Panasas Engineering has retained the strongest features of our classic storage blade design in Ultra, and the Ultra storage provides solutions to areas where the classic storage blade design could be improved. The Ultra is our next generation storage solution. An ASU 100/ASU extra large enclosure, it's the same enclosure, is a 4U enclosure that holds up to 4 ASU 100 or ASU extra large storage nodes plus 4 power supplies. Both the enclosure and the ASU node are manufactured by Supermicro. Supermicro configures these nodes with the hardware options that Panasas has chosen, but these are options that suit our Supermicro standard options, so they're not manufacturing them just for us. So the Ultra is still commercial off-the-shelf COTS hardware for lower cost of maintenance. So this is actually the manufacturer's photograph here. So it doesn't have our stickers, but you can see on the left here that we've got 2 nodes pulled out so that you can see what a node is. Each one of these are the 4 nodes. These 2 are both partially filled out. We have 24 3.5-inch SATA hard drives visible from the front of the enclosure, and 6 drive trays are visible from the front of each node. And if you remove a node, you're going to remove it from the front of the enclosure. This is a close-up of the nodes itself. The node numbers, you can see them here in this design, you can see them in the GUI, but if you look on the control panel, you actually can see the node numbers if you need to refer to it. These are the control panels on each side of the enclosure. There is a node release and pull handle right there. This is not floppy. These pull handles are floppy. All they are is to pull the node out. But the release handles, which are here, 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 and here for the 4 nodes, you push them down to release the node, and then you pull out on those along with the floppy pull handle. Numbering is 1, 2, 3, 4. And we're going to focus on the ASU 100 here. This is by far our most popular model. We have one installation of the extra large for a company that has a lot of really big files and wanted a higher, a little bit different architecture. We are not going to go over the flash storage in detail. If we have time, we will come back to that at the end of the course. Okay. Here's our storage node. It's a Supermicro Fat Twin, this number storage. And we're going to go over each of these things as we go. But that's what it looks like pulled out and laid on a table. These are the front of a particular node. The drives are numbered, again, from the left up and right up. They are not labeled on the node, but you can flash them. You see our little sticker there. Drives go 1, 2, 3, 4, 5, 6. Again, here is the release handle. Here's the floppy pull handle. When I say floppy, it means that you can push it back in if you wish. This node is not powered on, but if it were, you would see a blue drive activity and a red status activity for each one of these drives on the right side. Okay. What about the drive lights? The activity LED, which is the top one. If it's blue and solid, that means that the node is powered on and the drive is there. If it's blinking, we have I/O going to the drive, data access. If it's red and it's on for 5 seconds, that just means it's powering it up. If it's red and solid, that means there is a drive failure or warning. And if it's red and blinking, that means the storage administrator has asked the system to identify the drive. Talk about that later. The 6 SATA hardware drives store PanFS object data. The hard drives are 4, 12, or 16 terabytes each, depending on the node model. We have 12 terabyte drives in our lab system, the Demo Ultra Lab. You can see here that you can see here that I pushed this node, this release handle to the side. That pops out this lever. You can pull the lever to release the drive. Here's the back of the node. This is for the ASU 100. These are the networking and console ports, which we're going to go over later. There is a SATA SSD in this bottom port. In the 100 node, this top slot is empty. On the ASU 100 XL, both of these drive bays have more 3.5-inch hard drives, and the SSD is internal. This is a 2.5-inch Micron SATA SSD and is accessible from the rear of the node. It's either 3.84 or 7.68 terabytes, depending on the mode model. These can be hot swapped when the storage node is not activated. We'll talk about that later. Small PanFS object component data is stored on the SATA SSD. The fact that the small components are stored on the faster random access drives provides fast, small file system performance. Now, we actually are not going over this topic in this course. This is an advanced and long topic, but the customer slides are available to you if you want to read more about this. Here is the drive tray. The SATA SSD is installed upside down into it, so you pull it out, you turn it over, you see the drive. A 1.92 terabyte M.2 NVMe SSD is installed on the motherboard. This is an extremely fast drive. It's used to store PanFS OS and operating system files, the database for component metadata, and the metadata for the hard drive array. This drive is not accessible or replaceable in the field. If this goes bad, we replace the whole node. The ASU 100 nodes have two. This is the case for all of our nodes. Two 16 gig DDR4 EEC SDRAM dual registered dual inline memory modules. Big word, this is industry standard. This volatile memory is used for performance caches and system files that are held in memory. Volatile memory is not used for critical in-flight data. It's registered, meaning it has a buffer between the modules and the memory controller, and these take electrical load off the memory controller to increase memory stability. We have and always have had error correcting code. So that if the memory controller checks the parity of things in mean on every read, and it can correct a single bit data error. Errors that are more than 1 bit per word are uncorrectable, and if it finds one of these, it passes a call to the kernel to panic. I don't think that we've ever seen these on an ultra node. We had them sometimes in our very old hardware, but the code is still there should there be a more substantial memory blip. The double rate is the current industry standard, and we have 9 DIMMs on the motherboard that are not populated. They're not populated because they would not increase the performance any, so we've only given you the memory that the nodes can use effectively to hold down your cost. We have one NVR DIMM module installed on the motherboard. We'll talk about drop the R and just call it the NVDIMM for some simplicity. This provides, again, one EEC RDIMM. The SDRAM chips has NAND flash memory. We're going to talk about what that means in a little bit. We have a modular controller for the whole thing, and attachment for the cable to the PowerGem ultra capacity module. The life expectancy for these NVDIMMs is similar to the node itself. These store the critical intent and transaction logs. We'll talk about these more later. So here's this chip. It's in one of the DIMM slots. In the front here's how it connects to the node's power. These are the fast SDRAM chips. Here is our register, which operates the same way as the other memory to keep electrical load off. Here's the other side. Here are more fast SDRAM chips. This is the integrated controller that controls everything. This is NAND flash. This is a tiny little SSD that is on the chip itself. It's flash memory, and it is persistent. If the node loses power, everything on this little fast chip is saved. And that is where we store our critical in-flight data, and we'll talk about that more in just a second. This is the PowerGem Ultra Capacitor module. This is the top. This is with the top removed. This is kind of from the front. There is a power cable running through the node from the PowerGem to the node, so that if the node loses electricity, the PowerGem capacitor supplies the NVRAM with power long enough for this controller to copy this critical transaction logs to this flash storage. So what does this happens? We're just going to briefly mention this. You don't need to know this. This is just so you understand how your data is protected. When the node boots, the BIOS tells the NVDIMM controller to copy any intent and transaction logs that was on this persistent map storage on the chip into the fast SDRAM. These nodes boot a little bit longer. They stay in BIOS for about 3 minutes until this node is copied, and then all that data is erased on the persistent flash storage, because we want one and only one copy of that those logs. After the node is booted, the ASU accesses these records through the fast SDRAM. If the node reboots, shuts down, or loses power, either if it's a case of a graceful shutdown or a reboot, the BIOS tells the NVDM controller, or if the BIOS is lost power, it's not operational, the NVDM controller senses the power loss. The NVDM controller is still up because it has power from the power gem, and it copies this data in the volatile SDRAM to the persistent NAND storage. It's powered by the power gem, all this. So our critical records are not lost. Each of the ASU 100s contains one bronze 1.7 gigs CPU. The motherboard has two CPU sockets, but the second one is not used. And that's because if you have two sockets, you have to swap. The ASU nodes are not compute bound. We have found that one CPU is the highest value performance. CPU contains 8 cores and is part of the Skylake family that Intel is continuing to support. Right, let's go back around to the back. Here are our power supplies. Power supplies are 96% energy efficient. They automatically sense the incoming voltage and switch to support inputs in the range of 100 to 127 or 200 to 240 volts. So you don't have to make any adjustment from power supplies that were powered up in the United States, powered down, and powered back up in your country that uses the more European voltage. Have two power supplies on the left to power these two nodes. There's no electrical connections through the enclosure. It's this side and this side. So these two power supplies power these two nodes. They are redundant and load sharing if they're both operational. These two power supplies that are kind of in the middle power these two nodes on the right. Again, they are redundant, and if they're both up, they power them in a load sharing operation. So if you want to remove this, there's a little latch. Just pull it right out. This is kind of an unusual picture, but this is an actual photograph from me. This is why it's unusual. It's not professional or anything. The node and the power supply have been both removed from the enclosure. This is the front of the enclosure. Right there, you're looking into the socket for the power supply, and you're seeing the little bit of mid-plane that this enclosure has to connect the power supply to the nodes. And this node, you're looking all the way through the enclosure through the back, and you're seeing a whole nother another rack back there. This is just a hole there in the back. Okay, so let's talk about the LEDs on the power supply. They're green when all of these apply. The power supply is receiving power from the source. It's operating properly, and at least one of the nodes on that power supply side is powered on. It is amber when all of these apply. It's receiving power, it's functioning properly, and neither of the nodes on the power supply enclosure is on. The amber light means I am in standby mode. I'm providing standby power to the nodes, but I am not fully giving power to any nodes. The power supply is red if the power supply is not functioning properly, and obviously it is not on at all if the power supply is not receiving power from the source. The nodes, BMC, the monitoring, and the network operates even if the node has standby power. You may see some network activity LEDs blink when the node is powered off, just because there are stray little electrons going through the network, but the node is not actually functioning. Okay. A JSU node monitors its own hardware with an intelligent platform management system. It's called IPMI. This system operates independently of the operating system and PanFS. The BMC chip, the baseboard management controller, controls the IPMI system. It operates even when the node is powered off, as long as the node has standby power. If it has no power at all, obviously the BMC can't operate. It is powered off only when neither power supply, enclosure power supply has power. The BMC monitors the health of the CPU, the drives, the memory, and itself. And one BMC on each side of the enclosure monitors the power supplies on that side. The BMC interfaces with the operating system, the power button, the BIOS, and the IPMI NIC. And our software queries the BMC to be able to report hardware errors on the node. The BMC also controls the ASU node's cooling system. It monitors 11 temperature systems, including sensors for the CPU, the memory, the motherboard, and a whole lot of other things. It automatically adjusts the speed of the node's 2 fans to maintain optimum temperature. The air is pulled in the front of the node, expelled from the back. It's industry standard. And PanFS, the BMC will power down the node if the temperature reaches what the manufacturer has decided the shutdown temperature is for the node. We've decided we want it to shut down a little sooner than that. So we power down the node if the incoming air temperature reaches 40 degrees Celsius for 3 minutes. This is 104 degrees Fahrenheit. That's pretty hot. So not just a little blip. And we're not going to wait for the node to actually heat up. If the node's incoming air temperature is that high, it's going to get hot, so we're going to go ahead and shut it down. Okay. Now we're talking about the controls panel on the side of the enclosures. Each node's control panel is labeled. So there's one here for node 4. Under that, there's a node for node 2. And then on the other side, there are control panels for nodes 2. I'm sorry. Under this for node 3. On the other side, there are control panels for node 2 and node 1. There's the power button right here. This whole panel is controlled by the node's BMC. This power node controls the power for the node. It has a background LED when it is green, when the node is powered on. You can also use this button to power off the node. Powering off, we prefer that you power off the node through the PanFS operating system to ensure that processes shut down gracefully, but the NVDIM controller saves the critical data records regardless of whether the node is shut down gracefully or by software or powered off with the button. So it's really not a big deal. Everything that needs to shut down gracefully will because of the NVDIM controller. Once you power it down with this power node, the node still has standby power if both power supplies, unless both power supplies for the node are unplugged. This is the amber network LED to show activities on the network interfaces. This is the information LED. It either identifies the node or shows a node fault. And there's a recess button here where you can take a paper clip, stick it in that little hole and press it. And basically all this does is if you're in the front of the node and I say, I want to locate the back of this node, I'm going to press this little button and walk around to the back. You can. I've never seen anybody actually use this. Usually better just to identify the node through software, and both the light in the front and in the back will light up. The information LED right here, usually not lit. If it is in an error condition, it is the BMC that has set the error, not Panasas software. the PanFS OS should show the error because it queries the BMC for node status. If you want to identify the node, you can do that either with PanFS OS or IPMI. We'll talk about that later. There, in the back, there is not a dedicated identity light. The identity light on the back is actually on the motherboard, which is a little unusual, but it's very clear, can be very clearly seen through the rear grille near the VGA interface. PanFS OS and the IPMI are not aware of each other's activities to turn on the identity lights. So it's usually best to turn that the LEDs off or on using the same method that you used to turn them on, but it's not a big deal. It's just that if you turn them on one way and turn them off the other way, the GUI will tell you, for instance, if you turn them on with the GUI, you go find the node, you turn them off through IPMI, the GUI is still going to think those LED lights are blinking because it hasn't been told. No big deal. It's just going to show a little blinking light in the GUI and it's going to offer you to turn them off. If you do, it's perfectly fine. This is not a toggle switch. It just does the right thing. Okay. So what colors can the information LED be? If it's solid red, there's an over temperature condition. The node is hot, but is not yet shut down. Or actually, it will continue to show solid red if the node has standby power, which it will. If it's blinking pretty fast, we got a fan failure. If it's blinking more slowly, one power supply has failed. If it's blinking blue, you have asked the software to identify the node. And if it's solid blue, you've used a paperclip to press this button right there. You don't have to turn this off with the paperclip. Turning the node off, blinking off by software also turns that off. Out-of-band management. Sometimes we call this a console connection, but it's not always console. So in our technical knowledge base articles, etc., we call it out-of-band. We have two different ways. You can either connect a crash cart to the VGA port and a keyboard to one of the USB ports, or you can access it through serial over LAN. And we're going to go through the IPMI BMC NIC. Serial over LAN is also known as IPMI over LAN. The ASU node can use IPMI to control or query software on itself internally, even if serial over LAN has not been configured. This does have to be configured to turn it on. Both methods act as consoles and receive the same information. Our initial node configuration in the factory configures Grub to send kernel messages to both the VGA and the SOL interfaces during boot. If you want remote IPMI access, and some people do and some people don't, you have to configure it on every ASU node. We have a knowledge base article that tells you how to do that. We're not going to go over that here. Supermicro has set a unique IPMI password for every single ASU node because California law requires that. The California law, California, as most of you know, is a state in the western part of the U.S. Where Supermicro is located. This law is really intended for individual routers that they sell to people just at home, but it applies to these as well. The unique password is printed on the pull tab to the node's left edge, but we recommend that you use this configuration, overwrite that password with an IPMI password that you're going to have that's the same for every single node. Okay. And the way to do that is discussed in this article. You can also use the BMC GUI. You can access that through HTTPS. and then the IPMI IP. The IPMI IP is not the same as the node's IP. You configure the IPMI IP during the IPMI configuration. You're going to log in as the configured sole user. This is usually admin in caps, and then your password. Admin in caps is the default user ID. Okay. So this is what you see when you log on. You see a kind of a console. This is not what you want to use for console access because it's blurry and small, but you can at least kind of see that the node is on and get an idea of what it's on. Here's our IPMI password and user. This firmware revision is the BMC firmware. This redfish, all that's part of Supermicro's GUI. This is the BMC MAC address, and these are the actual network MAC addresses. Again, this IPMI address, that is the IPMI address, not the node's network interface IP. This is the bottom part. You see, it says host is currently powered on. You can power it down using this button. There are better options than the reset. So usually you just want to use the power on and power down. There's a lot of other pages in this BMC. We're not going to go over it in this course, so to save time. This is the same system page showing that the node is powered off. Remember, the BMC has power if the node has standard power, so you can use this to power on your nodes. Find to use the power on button. This will power up only this node, not the whole enclosure, not the whole realm. This is this is a page where you can also set the lights to blink. Again, probably better to access through a GUI, but if the node is not accessible on the network, you may want to use the IPMI GUI as well. You can also use IPMI commands if you wish, not from the GUI, but from a client on the management network. The operating system. The ASU 100 and XL and the Echo nodes on that's PanFS version 920 and higher, yes, run SUSE Leap 15.2. On the ones 911X and lower, it's SUSE Leap 15.0. We do support full operating system upgrades. We chose this operating system for its native CAL file system and mutable snapshots. We cover these in the certification course. Basically, this means that we can reconstruct the snapshots, and the snapshots are very efficient because of the operating system. The fact that the ASU node's Linux and not FreeBSD, as the director nodes and classic storage blades do, is mostly invisible to the storage administrator. The only exception is some network query commands. Review. So if everybody would unmute so we can discuss. Is Ultra Storage Node hardware designed and manufactured by Panasas?
Yes.
No.
It is not. It is not. It is designed and manufactured by Supermicro. We're not exclusively locked into Supermicro. We may provide hardware from other manufacturers in the future, but right now it's all Supermicro. What is the maximum number of storage nodes in an ASU 100 ASU XL enclosure?
Is it 4?
Yes, yes. I see a question. No, you cannot. You cannot use other OEM software. Our software has to know exactly what's on that node, and we have to have support for everything on it. Now, we might make if there was a lot of interest in having a Dell or Lenovo node, we may make a business partnership with Dell and Lenovo and put PanFS on it, but you personally cannot install PanFS on hardware other than these that we've provided. And you can't do it at your site either. We have to do it at our depot during our netboot process. That's a very good question, Gilbert. How many hard drives does an ASU 100 storage node have? No. More than that? Anybody know? Back
6.
6, yes, 6, all from the front. The extra large have 8. I don't think anybody has the extra largest, so I won't confuse the issue by talking about that. How many SATA SSD drives does an ASU 100 storage node have?
2.
I'm sorry?
2.
Now, one of them is not a SATA. So these are external, and I probably should say external there.
I think one at the back.
That's right. One external SATA SSD drive for an ASU 100. The ASF, the ASU extra large don't have any external, well, I'm sorry, the XL doesn't have any external SATA drives. The Flash has many SATA SSD drives. Yep. What memory device does an ASU 100 storage node use to store critical in-flight records?
Is it flash memory?
Yes, it is the NVDIMM. It is the NVDIMM, which is a combination of SD-RAM and flash memory. Not important for you to remember that. We're just mentioning it so you kind of get a little bit of an idea of our architecture. How are in-flight critical records saved if the node loses power or reboots?
And saved to the flash memory.
I'm sorry?
To the
Yes.
flash memory.
That's right. That's right. Very good.
Power cube.
How many power supplies does an ASU 100 or XL enclosure have?
Two on each side.
That's right. 4 total, 2 on each side, yes. How many redundant power supplies are available to each ASU 100 node?
2 on each side.
2 on each side, yes. So how many for each node?
So it's
2,
2
right.
per node, isn't it?
The nodes cannot see the power supplies on the other side of the enclosure. Which power supplies are available to which nodes?
And Jeep.
So the nodes on the left, where are its power supplies?
On the left.
That's right. It's side to side,
Yep.
not top and bottom. That's
Right.
pretty obvious, but I want to make sure everybody understands. What color is an ASU enclosure power supply, LED, if the power supply has power but is not functioning properly? No.
I want to say red.
Red, bright red, fire engine red. What color is an ASU enclosure power supply if the power supply is functioning and is generating standby power to both nodes on its side of the enclosure?
Amber.
Amber, yes, this one's amber. Amber is fine. It means the nodes are not on, but I'm good. Red is when there's a problem. What chip monitors an ASU 100 storage node's hardware?
As the BMC chip?
That's right, it's the BMC. Name two methods to access an ASU 100 storage node out of band.
Remote or
I'm sorry, I didn't hear you. IPMI Sol, that's one, yes. What's the other one?
serial over LAN?
Say it one more time.
Serial over LAN?
Yes, that's one of them. There's one other way. Kind of old-fashioned.
Serial connection?
You just
GUI?
connect old-fashioned crash cart. All these IPMI, I'm counting as one. The other thing you can do is just attach a monitor and a keyboard to the VGA ports here and back.
Okay.
This is usually not a whole lot of fun. There's the VGA port. I mean, it's fine, but you have to be there. You have to be there to do this. For IPMI, if you've got it configured and up, you don't have to be there. Does failing to configure an ASU 100 storage node's IPMI serial over LAN networking disrupt the ability for PanFS OS to monitor that node's hardware? No, it's fine. It just means that you don't have remote access to the node except through the network. Can an ASU storage node's BMC be accessed by IPMI serial over LAN if the node is powered off?
Yes.
Yes, it can. And I took this away from the slide. I'm trying to shorten it up. Can the storage node be made non-functional by changing some of the configuration options using the IPMI GUI? I think the answer to that is kind of obvious. Please don't change the configuration. Yeah. All right. Questions on this?
Yeah, I have a question. If we were to have a hardware failure, would we go to Panasas for support or Supermicro?
Panasas.
Panasas.
Panasas. That's that is a very good question. If you buy a switch from us, a Mellanox, a Supermicro, anything else, you also come to us for support. Now, if it's a very difficult problem, we're going to kick it to the vendor, Mellanox, NVIDIA, Supermicro, but we're going to still act as the intermediary. So your contact for support is all Panasas.
Okay. Thank you.
You're welcome. Any other questions? All right. Let's take a 10-minute break. come back at 19 after the hour, and we will talk about the director note.